let's jump right into one of the weirdest little secrets in all of biology. It's a story that involves two things you see every day, a potato and a piece of paper. And the crazy thing is they're almost identical, but that tiny almost is what changes everything. And it all comes down to shape.
So here's the big question for today. You can eat a potato and get all that starchy energy, no problem, right? But if you try to eat the paper it might be wrapped in, well, good luck with that. It just passes right through. So what's going on here? How can one be food and the other is just fiber? Okay, and this is where things get really weird. I mean, on a molecular level, the main stuff in a potato, that's starch, and the main stuff in paper, cellulose. They're both built from the exact same little building block, a simple sugar called D-glucose. Think about that. They're made of the same bricks, but one is a source of energy and the other is, well, not. So how is that possible? To figure that out, we got to go back to the beginning. All right, to crack this mystery, we first need to get a handle on what these molecules actually are. Let's start with the absolute basics. So, carbohydrates. They're one of the essential molecules of life. The name itself kind of gives it away. Carbo for carbon and hydrate for water. Now you'll see the technical definition here, polyhydroaldehyde or ketone, which I know sounds super complicated, but all that really means is you've got a chain of carbon atoms and they're just covered in these little alcohol groups. That's it. They're the building blocks for both fuel and structure for pretty much all life on Earth. And where do these things even come from? Well, you can thank the sun. Plants are basically magic. They're like these tiny solar-powered factories. They grab carbon dioxide out of the air, slurp up some water from the ground, and then use the energy from sunlight to stitch it all together into sugars, like glucose. So yeah, every potato you eat, every piece of paper you write on, it all started its life as a bit of sunshine and air. Okay, now we're getting to the real core of this. See, it's not just about what a molecule is made of, it's about how it's all put together. In chemistry, shape is everything. And that brings us to this super important idea, isomers. The best way to think about this is with Legos. Imagine you have a handful of the exact same bricks. You can snap them together one way and build a car. Or you could take those same bricks, rearrange them, and build a house. Same parts, totally different result. Well, that's what isomers are in chemistry. Same chemical formula, just a different arrangement of the atoms. And that tiny change in arrangement, it can give the molecule a completely different personality. And just look at this example here to see how subtle we're talking. On the left, D-glucose, and on the right, D-galactose. They have the exact same atoms, C6H12O6. The only, and I mean only, difference is which way one of those little OH groups is pointing. That's it, just that one little flip, and bam, you have a totally different sugar that your body treats differently. This is a huge theme in biology. Tiny changes in shape have massive consequences. So we've been thinking about these sugars as straight little lines of atoms, but that's not actually how they hang out most of the time. You see, when you put them in water, which is, where most of life happens, something really cool happens. They fold. Yeah, so when a glucose molecule is just floating around inside a cell, that straight chain form isn't very stable. So what does it do? It basically bites its own tail. The alcohol group way down at carbon 5 swings around and attacks the aldehyde group at carbon 1. And when it does that, snap, the whole thing closes up into this really stable six-sided ring. And right here, this is the whole ball game. This is the key to our entire mystery. When that ring snaps shut, that brand new alcohol group on carbon 1, it has a choice. It can either point down or it can point up. If it points down, we call it alpha glucose. If it points up, we call it beta glucose. That's it. Same atoms, same ring, just the direction of one little group. But that one tiny difference, that single switch, is what changes absolutely everything. And what's really interesting is that nature actually has a favorite, the beta form, the one where the group points up. It turns out to be just a little bit more stable, and because of that, it's more common. If you had a glass of sugar water, about 2/3 of the glucose molecules in there would be in that beta form. And you should definitely keep that in mind, because it helps explain why nature loves to use it for building strong stuff. Okay, so now we have our two different Lego bricks, right? We have alpha glucose and beta glucose. So now let's see what happens when plants start linking them together chain after chain to build these huge structures like starch and cellulose. So when a plant needs to store up some energy for later, like at a potato, it grabs thousands of those alpha glucose units and starts linking them together. Because of the geometry of that alpha bond, the way it points down, the whole chain just naturally starts to twist into a spiral, like a coiled up spring. It's a perfect example of shape-creating function. This coil shape is awesome for packing a ton of energy into a really tiny space. But what if the plant isn't trying to store energy? What if it's trying to build something strong, like a cell wall or the trunk of a tree? Well, then it reaches for the other brick, beta-glucose. When you link these guys together, that up-pointing bond forces the chain to become dead straight, a perfectly straight, rigid rod. And then these rods can line up next to each other like little planks of wood to form these incredibly strong, fibrous sheets. That's what wood is. That's what cotton is. And yep, that's what paper is. So this table here really just lays it all out, side by side. You've got starch made from alpha glucose, which makes a coiled chain, perfect for storing energy. And then you've got cellulose, made from beta glucose, which makes a straight, fibrous chain, perfect for building structures. And that brings us right back to that last row, human digestion, digestible versus indigestible. So why? Why can we break one down but not the other? Okay, it is finally time to put all of these clues together and solve our original potato paper mystery.
So we've seen it, right? They're both just chains of glucose. The only difference is how they're linked. So what is the big deal? What is it physically that stops our bodies from snapping those beta bonds in paper?
Well, the answer is all about our enzymes. Enzymes are these tiny little biological machines in our bodies that run around breaking molecules apart. And they are unbelievably specific. The best way to picture it is a lock and a key. The enzyme is the lock, and the chemical bond it's supposed to break, that's the key. And if the key isn't the absolute perfect shape, it's not opening that lock. And that's precisely the problem we have here. Our digestive system makes enzymes, like amylase, that are shaped perfectly to fit the alpha bonds in starch. It's the right key. It slides right in, snips the bond, and frees up that glucose for us to use as energy. But when that same enzyme bumps into a beta bond in cellulose, nothing. It just doesn't fit. It's the wrong key for the lock. The enzyme can't get a grip, so the bond stays intact, and all that energy in the cellulose just stays locked away, completely inaccessible to us. And this quote here really just nails it. The only chemical difference between starch and cellulose is the stereochemistry, which is just a fancy word for the 3D arrangement of that link. That's it. This huge biological difference, what separates our food from indigestible fiber, it all comes down to the geometry of a single chemical bond. It's just a wild example of how, in the world of molecules, shape is destiny. So the next time you're eating fries or just reading something on a piece of paper, take a second to remember the simple, elegant story of alpha and beta glucose. It kind of makes you wonder, doesn't it? What other huge, important differences in the world all around us, from how our medicines work to the very fabric of life itself? What other things boil down to nothing more than a simple little switch in molecular shape?